In this problem, we are given the following circuit diagram here. We are also given a phasor current, I of A, is equal to 2 with our angle of 0 degrees, and we are asked to find the following phasor values for our I of B, I of C, and V of G. To start this off, I'm going to plug in what we know. We know that our I of A is equivalent to a 2. This is going to be for the polar form and the rectangular form. It's just going to be 2, and we can see that if we convert it either way. Now, we know that the voltage going into our I of A, or the V of A, is equivalent to the voltage going through our I of B, which is going to be our V of B. And they're equivalent because voltages in parallel are the same. So what we can do is find the voltage, since we are given the current, and then set that equal to the voltage of our I of B, and since we're given the resistors for our V of B, we can find our current for B. First, we're going to solve for our V of A, which remember is equal to our V of B because impedances in parallel are the same. I use impedances and resistors kind of interchangeably, but since we have an inductor and a capacitor with resistors, we should call them impedances. Now, I'm going to start this off by saying that our V of B is equal to our V of A, and we know that we are going to have the current, which is our I of A, so 2 times our impedance. And our impedance is 50 plus J of 150. We have the resistor plus the inductor. If we factor the 2 in, we're going to get 100 plus J of 300. And this will be the rectangular form for our V of B. Now we need to solve for our I of B. We know that our I of B, using Ohm's law, is equal to the voltage of B divided by the resistance or impedance at B. So we're going to say Z of B. We know that our V of B is this that we found up here, so we're just going to plug this in, and we're going to divide it by the impedance, and this is the impedance at B, so it's going to be this resistor and this capacitor. Now, before we divide these out, we need to convert them to polar form before we divide. To convert a rectangular to polar form, what we're going to need to do is have our Vmax equal to the square root of our real number squared, so this will be the 100 for the numerator, plus our imaginary number squared, which is the 300 for the numerator. And to find our angle, we're setting this equal to the tangent -1 of our imaginary number divided by our real number. And we're going to do this for both the numerator and denominator. And after we do that, we're going to get these two equations. Remember, for the numbers, we are going to divide these two, while for the angles, we are going to subtract the denominator from our numerator. And if we do this, we're going to get our magnitude to be 2.5 with an angle of approximately 90 degrees. And this will be the magnitude and angle for our I of B. Now we need to still find I of C and V of G. We know all of the currents. We know this I of A, we know our I of B, and we know this current right here. If we add them all together, it's going to equal I of C. We know this because there is some current flowing through this part. And since this node right here breaks into parallel, we have some current going this way and some current going this way. Well, if we add the currents at this node together, we will get this current. We recently found our I of B to be this 2.5 with a 90-degree angle, and to this we are going to add our 6 plus J times 3.5. Now to add these together, we are going to have to convert our I of B, which is this current, into the rectangular form. To convert from polar to rectangular, we are going to have our number, and then a parenthesis, cosine of our angle plus J times the sine of our angle. This is going to give us a 0 for our number, and then a 2.5j, or j 2.5, for our imaginary number. And to this we are going to add our 6 and j 3.5. If we combine like terms here, we're going to get a 6 plus a j 6. And this is going to be the current that is flowing through this part. Now, for I of C, we know it's going to split in this way, because the current is going to be in parallel at this node. So we need to add the current that is going downwards and the current that is going the other direction. They add together because, again, they are parallel, which splits the currents at this node. We know the current going to the right is the 6 plus j of 6, and we know the current going downwards is our I of A, which is equal to 2. So we can just add these together. We're going to have 2 plus 6 plus j of 6, and this is going to be equal to 8 plus j of 6. So this will be our current that is equal to our I of C. Now our answer wants it in polar form, so we're going to then have to convert this. We are going to use these equations up here to do so. In doing this, we're going to get that our IFC is approximately a 10 magnitude with an angle of 37 degrees. And if I reveal the answers for IFC, we can see that is exactly what we needed. Now we're going to solve for our V of G. We're going to do this a little bit differently. We are still going to solve for current, and we are going to say that our I of C, because remember this is the current flowing over our V of G and V of A, is equal to the voltage, which will be our source voltage, V of G, minus our V of A, and this will be divided by 5. This is a formula that we learned in Intro to Circuit Analysis, and it's where we have this current set equal to the voltage here over the impedance or resistance that it is over. And then I also marked the directions of our voltages. We can see that they're going in the same direction, so that is important to note. And now we can start plugging things in. We know that our I of C we recently just found to be a 10 at angle 37 degrees. So we are going to plug this in and then multiply this 5 to this side. When we do this, we're just multiplying the magnitude. We don't mess with the angle when we multiply something in. So we are going to have a 50 with an angle of 37 degrees. Now we have our minus 5a on the right side with our VG. We want to get our VG by itself, so we'll add V of A to both sides. And we know that our V of A is this 100 plus J300. We found that out earlier. So we are just going to have a plus 100 plus J300, and this will all be equal to our V of G. Now, to add two equations like this together, we need them to be the same thing. So we need to convert this polar form from polar to rectangular. And we are going to do that with the red equation that we wrote out earlier here. If we do this, we are going to get 40 plus J of 30, and we can add it together with this part right here, and then combine like terms. After we do that, we are going to get this equation here, and the answer wants it in the polar form, so we're going to have to convert it using the gray formulas that we wrote over here. And remember, when we are converting from a rectangular to polar, it's important to graph this to make sure we get the correct angle. We know that our imaginary axis is the y-axis, and our imaginary is positive, so it'll be up here. Same thing for our real number, however, it's going to be in the x-axis, which is over here. That means our angle has to be inside of quadrant 1. If we plug these into the formulas that we just were told to do, we are going to get the answer of approximately 358.5 for our magnitude and 67 degrees for our angle. And that is how you would go about solving this problem. If you want more network analysis problems or notes that cover this material and the entire coursework for this subject, they will be linked in the description below the like button.